this talk is similar to the goal of the true previous talk. We want to describe higher order computation where there's a classical quantum interaction because we want to control the flow of what we do with quantum data using the classical data. So if we want to study this, we need to construct, we need to have some language to study. The usual design idea is to add a qubit type to a lambda calculus and to add rules, typing rules to the calculus to take into account important quantum mechanical phenomena. Well, for example, no cloning. We have heard this in the two previous talks. If we want to take into account no cloning, we want the qubit to be used linearly, so we cannot duplicate them. And if we want to be able, if we want the language to be able to take into account entangled qubits, we need a special type operation, tensor type operation, which is different from the classical product operation. So that's the basic line of thought we have. So ideally, we would like to validate the construction, the type system we construct, with a soundness result, where we interpret our language and types using some quantum mechanic formalism. So that's the plan. But there are problems. So interaction of tensor and lambda abstraction with lambda abstraction are complex. As you can see, there are 3 talks in this workshop about quantum lambda calculus, and we have 3 different type systems, 3 different ways to think about things. So if we add this linearity hypothesis to the language, constraint to the language, well, we know there will be no duplicating of qubits. But for example, one question that I asked myself when I designed the language I will present in a few minutes, should abstraction over part of a tensor product of 2 unknown qubits be allowed? To be able to model this, we need some sort of adjunction in the model, which for now is unspecified, which would take function taking 2 qubits, possibly entangled as input, and return, for example, 2 qubits, and a bijection between this kind of function and the function taking 2 separate qubits. You cannot hope to have something like that in any good model for quantum computing. So that's a part of the obstacle. Another problem is that we need some sort of mathematical model which describe formally both classical and quantum operation. In a way, there's a lot of research in that direction. We don't have a good model which, if we forget the quantum part of the model, would specialize to a known model of classical lambda calculus. So what I propose is, instead of using a tensor operation between qubits, I introduce a family of qubits. So the tensor is built in the qubit type like this. So this way, there's no abstraction over part of a qubit in the language. And on the semantics side, I will construct, I will outline the construction of a dimensional semantics based on dialogue games, where we model a quantum classical interaction as interaction between system and environment. So this is based on the successful ideas in the classical semantics, and this kind of semantics has been used to model many different languages. So I will show how to adapt this to quantum computing. So the language I work with is a simply typed lambda calculus with quantum data, QDL for short. So the basic syntax is standard lambda calculus, but I will go over the new ingredient and I will give some examples of terms, interesting, simple terms, for you to get a taste of the syntax of what we can, what kind of program we can code in this language. So one ingredient, important ingredient I had to add is extended variables. So since my qubit types represent tensors of qubits, I need a way to refer to a specific qubits in a tensor. So the variables I use formal tensor of variables like this, so I can point to a specific qubit in a tensor. Of course, since it's a lambda calculus with quantum data, I can add a quantum state. Now I allow to use any density matrix. I put a tensor product of terms, so there's no tensor product type operation, but I can take two terms and tensor them. Unitary operation, of course, this is necessary. And measurement. The measurement syntax is a bit strange, maybe, but it was necessary, so maybe I should explain it. The measurement syntax is to be read like this. We measure qubit I in some term m, and we store the result in some classical variable b, and what remains of the qubit is stored in some extended variable like this. And these results are accessible locally in n. So this kind of local access was necessary to to avoid some problems with side effects of measurements. And also I have a 1 qubit measurement. Just a technicality, but so this is rich enough to encode any quantum circuit. It's quite easy to code, to translate the quantum circuit in that language. For example, this is the program for teleportation. So I won't go over this in detail. So let's look at the type system of the language. So it's standard lambda calculus types. I have Boolean type, the standard arrow and product operation, and this family of tensor qubit types. So there's no tensor, I insist, there's no tensor type operation. Typing rules. Okay, so there's a lot of them. Many of them are just classical rules, and I want to focus on the 3 tensor rules. So that's a new feature, maybe, of this. An interesting feature of this language is that I had to use 3 different tensor rules depending on the situation. So I will explain them by forgetting about context and focusing on what's important. So in the first case, if I have 2 qubits, let's say we have 2 density matrices terms, I can tensor them and I get something of this type. In the second case, if I have 2 qubit variables and I tensor them, I have to tensor the qubits in the hypothesis too. So that's because of the problem with adjunction I pointed to in my introduction. And in the third case, I have 1 qubit variable and 1 known qubit. And this is, if I tensor these 2 things, I get something which takes a qubit variable and produce an augmented qubit. So basically, this is preparation of a. This is just adding an NCA qubit in a known state. So these are the most simple example of the 3 rules. Things get a lot complex when we add the conditional into these, and so we can have conditional preparation if we Boolean value is 0, then we prepare some, we tensor with some density matrix and get tensor with some other density matrix according to the value. These three tensor rules are closely reflected in the semantics I will give in a few minutes. So, well, I will go over quickly the operational semantics. So this is just a rewriting system to interpret all this, which tell us our terms reduced to values. So values just like qubits and booleans and base value like this. So this is a probabilistic reduction, of course, because measurement we will reduce to different values probabilistically. So here are the rules. Most of these rules are quite straightforward. They are classical lambda calculus rules. And the quantum part is also straightforward, and just what you would expect from quantum mechanics. So the denotational semantics I give in the paper is based on games, on dialogue games, like I said, and follows the usual game semantics ideas. So to summarize this idea in a kind of slogan form like this, the types of the language are interpreted as games. I will explain this in some details later. The terms are interpreted as strategies, and the reduction process I did go over quickly with the operational semantics will correspond to composition which reduce the complexity of the strategies. So the terms are interpreted as arenas, which is just a name for a game where we don't care about who wins or loses. So the arena just fixes the rules of the dialogues, which will be used to interpret the types. So for example, the bool type is interpreted as a dialogue where the environment wants to know what is the Boolean value, and the system just answer with a Boolean value. So the opponent asks questions and the player just gives answers. The data itself is represented as strategies. So the arenas represent the types, but not the precise value, because just the Boolean arena does not tell you, does not tell us how player will answer the questions. So we don't know what is the actual Boolean value. So the value are presented as strategies. For example, the strategy true will make player answer the initial query with 1, the true value. So and there can be repeated question. The strategy can be probabilistic. This is necessary since we want to model the result of measurements later. So we have to use probabilistic strategies. As the types can be combined to create more complex type using types operation, the arena, which models them, also can be combined to produce more complex arenas. The product arena just allows the opponent to choose, for example, which Boolean value he wants to know about, and player must answer to the question in the right arena. The arrow operation is more interesting, allow to represent functions. So the opponent starts by asking what's the output of the function. Player will answer, well, if you want an output, give me an input. The opponent has to produce the input, and then player can answer the initial question by using the provide input to produce the output of the function. So each strategy for player in this arena will correspond to some function from bool to bool. And the final ingredient, the one which is used to model the reduction process is compositional strategies. For example, if we have two knot strategy like this, we can reduce them to an identity strategy. So this is the this can be described like this. I'm just giving the idea with bools, but all this can be defined for any types. So what happened? We follow the same idea as not is just a strategy which decides a function. So opponent start by asking for the output here. So player will ask for an input for this not function. But now player wants to use this other strategy. So what he will do, he will consider this as an initial move in this arena for this strategy. So he will just ask for an input for this not function. He will receive some input from opponent. He will apply he will negate this because player is using the not strategy. Then again he switched the roles. He switched sides, and then he will consider this as an input for this not function and negate this input to give the answer to the initial question. So if we just hide the middle interaction, what we get is the identity strategy, which corresponds to the identity function. So this is the kind of idea that can be adapted to describe quantum computing. So we need to introduce a quantum arena. So suppose H is some finite dimensional Hilbert space. The quantum arena works like this. We follow the same kind of idea that is used for the Boolean arena. So opponent will ask for some measurement. Will ask a measurement. Will ask for some measurement result. Opponent can choose any measurement he likes, and player has to provide the measurement result. So what kind of measurement are we going to use here? There are many measurement formalism, and I found out that the most convenient one is quite abstract, but is quantum interpolation. So quantum interpolation is just a family of superoperator indexed by measurement result. Each of these superoperators start from the same space, but can go to different spaces. And we add this condition just to make sure that the probability of getting some measurement results sum to 1. So if we start in some initial state and we measure it with some quantum iteration like this, the final state will be obtained just by applying the corresponding superoperator, and this happened with this probability. So the quantum arena, now we have a more formal, more complete description. The opponent questions are quantum iterations. We can describe states in these arenas. The states, the state strategy, for example, for some state row, will make player answer the quantum integration question using what we would expect from quantum mechanics, using the probabilities I just described. So, for example, using the strategy rho, player will answer M1 to this initial question with this probability. And if there are many questions asked in a row by opponent, of course the state is updated each time. So measurements, this quantum integration affects the states player used to answer the questions. This arena, this quantum arena, allow non-quantum strategy. For example, the strategy which always answers 0 for any quantum integration. So this is not describing, but all the strategy that we use to construct the notational semantics of the language R quantum. It's also possible to define a strategy which describes a superoperator. So if F is some superoperator, the strategy is as follows. Opponent asks for some the result from the measurement result of some quantum iteration like this. And the trick here is a little different. Instead of changing using the input and to provide the output, the answer to the initial question, we modify the question. So player will ask in the input arena a modified question, which is this is just composing every superoperator in E with the superoperator F. So this way we can prove that if we compose using the composition of strategy I described earlier, the strategy corresponding to F with the strategy corresponding to some density matrix rho, then we get the strategy corresponding to F of rho. So this is a kind of sumness result, a small sumness result, but this is the key idea that makes all the semantics work. Just to point out how this is related to the problem I described in the beginning of this talk. Suppose we have we want to describe some strategy which separates qubits. So takes a qubit on some tensor product of two qubits and produce some separated qubits with the classical product represented by this arena operation. An initial question would be in one of these two arenas, and player have to produce an answer to this question using a question on the tensor product here. But this is easy to do. We can take this quantum iteration and extend it to the second, to take into account to produce a quantum iteration on both spaces, on the tensor product of the two spaces. And player would just copy the measurement results he gets. So I didn't put that here, but it follows the same pattern as the other strategy. But if we want to use this idea, but in the other direction, so we have two separated qubits, and we want to produce some qubit on the tensor product, then we are stuck because we cannot take a quantum iteration, a measurement on the tensor product, and produce a measurement result to this by measuring separately the two input qubits. So with this idea, we can construct additional semantics for the language, show the types are interpreted using, well, these are the direct interpretation that are usual in game semantics, except for the qubit, the interpretation of qubit, which is given by the ideas I just described. The terms are interpreted as strategies. And I will describe the key ideas which allow us to interpret the tensor operations and the measurement operation. These are the two most interesting. So again, I simplify. I take a specialized case, but it's just to allow you to grasp the important ideas. So if we have two known qubits, so that's one of the three tensor rules I gave earlier. So so we have interpretation of these two terms. We have strategy corresponding to these two terms, and we want to produce something which a strategy in the tensor product here. So opponent can start by asking for any quantum integration over the whole space here, and player have to answer this using to construct an answer, to choose an answer here, but using the strategies already defined here. We are thinking, well, I should have said that from the beginning, but this is an inductive definition of terms. So at this point, the definition, the definition, we assume that we already have strategies to interpret M1 and M2 here. So the key here is to note that these two strategies, this is a strategy which produces a qubit here, this is a strategy which produces a qubit here, and the answer will be given by some density matrices. Using the probability of giving some measurement result answer are computed using these density matrices. These are built into these strategies. So we can just answer to the two density matrices, and this gives us the right state to compute the measurement, the probability of giving the measurement result M here. If we have two unknown qubits, so that's the second case. This is the scheme is a little different. Because here M1 and M2 are two strategies, but M1, for example, is from this arena to this arena, and M2 is from this arena to this arena. And M1 corresponds to some superoperator. That's something that can be inductively assumed. So suppose F1 corresponds to M1 corresponds to F and M2 corresponds to J. Well, we have to modify the initial quantum interpolation question to produce a quantum interpolation question on the tensor of the two inputs qubit. So we have to tensor the two corresponding superoperator here to modify. So this is similar to the scheme I described earlier for superoperator in general. But this is different. This is not the same as this is not the same as for known qubits. For measurement, there's something interesting going on. We need a strategy which measures qubit I in some tensor product of qubits here of this form, in this arena. So this is necessary in the definition. So we must, if opponent can choose to start here or here. If opponent start here, by asking some quantum interpolation question here, player have to produce some question here. And since measurement are measurement in the canonical basis, the computational basis, sorry. Well, we can just extend this question to a question into the larger space here by measuring the qubit I in the computational basis. This will give us, then opponent will have to provide measurement result for this part and this part separately, and the question here will be answered by M. And if later opponent wants to know the bit here, the Boolean value here, well, it already has been provided here. But interestingly, if opponents start directly by asking for the Boolean value, so for the measurement result in the computational basis, the only thing we can do here is to ask to measure the qubit I in the canonical basis and leave the rest alone. So we'll get some Boolean value, player will copy it to provide the right answer to the initial question. Later, opponent can decide to ask for to measure the rest of the qubits in some way. And now we have to measure this qubit again. And that's the only place in the semantics where we have to measure 2 times a qubit. And in game semantics, this is well known. When we measure 2 times a qubit, there are side effects, like I said when I described the strategy for a density matrix. So, and when there are side effects like this, when one answer, the way we answer here depends on the way we answered earlier, this is known as thread-dependent strategies. So the qubit strategy must be thread-dependent because we have to measure them 2 times in this case, and that's the only place in the semantics where this happens. And because of this, thread dependence is known in game semantics to produce, well, thread dependent strategy are not duplicable. There's a duplicating strategy, and thread-dependent strategy cannot be duplicated, and this is why we need linearity in the language. So this is not the same reason. I didn't use the no cloning argument here. I said we need linearity because we need at some point in the semantics to measure 2 times because measurement have side effects because of entanglement. So this is a different way to think about that. So, well, I proved, let's go over this quickly. I proved the soundness result with the semantics. So, using quite a standard argument, except for some details. And this is, in a way, this is simple, but in a way, this is why it is exciting. Because the semantics is derived from a well-known semantics for classical language, and the arguments are similar. So this is quite a simple way to work with a quantum number calculus. So maybe okay, I don't know what to say. Just quickly, it was mentioned earlier that there are 2 ways to work with quantum lambda calculus, either to put quantum state directly into the language as terms, or to have reference to qubits. So that, and with Prakash, we presented in MFPS earlier this year a quantum star approach to which use the same kind of idea as semantics, so the same kind of game-based dimensional semantics, but we have reference to qubit. There are no, in the language, there's no linearity at all, because references, we can have as many references to the same qubit as we want. I mean, referencing many times to a qubit is not the same thing as copying. So, yeah, well, some idea for future work, adding recursion to the language, full abstraction, but this is something. This is why usually game semantics is used in the classical language, and it would be nice to get some full abstraction result for these quantum languages, but we need some characterization, we need a more tight characterization of these quantum strategies. Yeah, and also how these quantum arena and quantum integration strategies have some nice categorical properties, which needs to be studied in a more detailed way. Okay, so that's the end.
Are there any questions, comments? Yes.
So one of the interesting things you showed was that you could define strategies which would violate quantum mechanics.
Yes.
So do you see any use for that in studying some more general theories like what Alex was talking about earlier today?
I don't know. I mean, these are, in general, these are just probabilistic strategies, but I was not interested in I was interested in using the quantum strategies to model quantum language, so I don't know how they can be used to.
But just a remark, probably the more interesting thing is to figure out a characterization of exactly the ones that are physically realizable, to see what are the conditions that rule them out. So that's the obstacle to full abstraction. Yeah. It's not the usual lambda calculus nonsense. It's the, you know, what is physical and what is not. You don't have a good abstract characterization of that.
We have already such a characterization for the qubit strategies. So the quantum state strategy can be characterized using Gleason's theorem, and a variant of Gleason's theorem for quantum integration. So I have such a result. But the problem is superoperators. Superoperator strategies are harder to characterize.
Yeah, well, it was along the same lines. Like, what I would think is the interesting thing is really using game semantics, the whole mechanism to produce, say, categories, models of whatever kind, and then like evaluating which sort of physical constraints sort of force in the direction of real quantum mechanics. But obviously, you're going to get very different kind of models, and it would be interesting, like whether you get models, for example, also without byproducts again. Or something like that. I'm so against byproducts.
You can't buy a product to save your
sell products. Sort of buy.
I didn't get whether you had additional semantics for just abstraction and projection.
No, it's for the whole language.
For the whole language.
Yeah.
So is it, I mean, is it setting your expired? Or is it? Okay, the data didn't get maybe I can ask.
Okay.
Any more questions? Yeah, Yannick, is it alright if we don't clap for you a second time? Because I'm really tired of clapping. You don't need the validation, do you? I mean, I'm just kidding.